Okay, time to start. It is officially time to start the class. And okay, so by popular demand, I've had a request to go over assignment number 2. So I'm going to do that. And if we can quiet down a little bit so I don't have to yell so loud, that'd be good too. And a few, before I even start, let me go through a few administrative things to start out with. There's a roster going around that you need to sign as usual. That's item number 1. Item number 2, so next week, I'm going to introduce the midterm to you. The midterm exam is going to be a take-home exam that is going to have you do something. I'm actually kind of thinking about doing something risk assessment related, actually. It'll be a project/assignment. It won't be multiple choice or fill in the blank or something like that. It'll be some activity that you'll have to do. And the midterm will be due within about 3 to 4 weeks or so. I haven't written it yet, so I don't know exactly what I'm going to do for you. But we'll find out next week. So I'll be posting it out on bhacker.com. We'll have it in the ITU EMS. We'll have it ready to go. And don't worry, because immediately people start going, well, it's due in 3 weeks, but what if the ITS is broken? And what if, don't worry about it. It won't be counted late. What we want to do is kind of get it out, get you to do it, turn it in before the end of the course. It's, sometime, in the middle, it's a midterm. It's supposed to be done in the middle of the class, right? So the other thing I'm also going to have available for you next week, and I'll talk about, is the CSLO. The CSLO is not written for this course. It's not going to be, because I know as soon as I say the word CSLO, so if all your faces just drop down. Don't worry about it. It's not like the CSLO in the old days. It will be an essay, but it won't be like, tell me how you feel about software engineering. How does software engineering make your neighbor feel? And what did you learn about software engineering? And how are you going to use software engineering? And all those other crazy questions we were asking you. It's going to be something like, a business problem or a software engineering 2 related thing. I'm actually kind of thinking about like maybe dependability or reliability or something. Some assignment where you'll have to like assess some measurement between two different systems. Tell me, doing an analysis or something like that. That'll be a hands-on kind of exposure to software engineering concepts, of what we've been talking about so far. Anyway, so if you have any questions about that, I can entertain them, but nobody ever has any questions, so we'll move right along. Unless you have questions now, speak now, or wait. I'll entertain them after class. Okay, good. And so that'll be all about next week, so don't ask me yet. It's not available yet. It will be posted, and I'll go through it, and I'll explain to you what you need to do for it, just like I'm going to go through assignment number 2 right now. And all right, so assignment number 2. It says develop a risk assessment plan. For those of you who have not taken software engineering 1, you're going to need a little bit more. You were in the software engineering 1, weren't you? Yeah, so you should have this already. The guy who asked about it has already been in that class. There is a document that I have out on bhacker.com in the software engineering 1 section. And if you can't find it, send me an email. I can send you the link to that document. It's 160 or so pages. It's called SE Notes or something. You'll find it in the independent study list where you'll see software engineering 1. It will go in how to develop a risk assessment plan. It shows you, the example actually shows you a template that has a box, has a chart in there where you number the risk and you put it into a category and you identify certain characteristics about it and you have contingencies and a bunch of format for it. You don't have to use that, but some students who haven't taken software engineering 1, who have not been exposed to that, are going to be looking at this going, what do I do with this? And so I'm going to give you some options that you can take to do this assignment. And if you don't want to go through, if you want more information, the reason why I mentioned the one from Software Engineering 1, it's great background information. It'll fill in the details of how to do a risk assessment and what a risk is all about. It's everything you ever wanted to know from Software Engineering 1 but maybe didn't get. So look for that link. It will be right next to the syllabus in Software Engineering 1. It'll say SE Notes or something on it. And towards the end, in fact, it's just a Word document. Just do a search on risk, and it'll take you. There's a whole entire, like maybe 20 pages on risk in that document. So it's everything you ever wanted to know. If you go on the internet and you search, you're going to find too much information. It's not necessarily going to be on the concept. It's going to be on examples that you'll probably end up finding. So what do you need to do for this particular assignment? It is not based on assignment number 1. Assignment number 1 has you identify some certain things, but it doesn't talk about, in fact, I think at the bottom it says, wait for assignment number 2. You don't have to do a full risk assessment. So you don't have to do this for number 1. Number 2 says, for this assignment, you're going to produce a risk management plan for a project of your choice. You can do a project that you're working on. So let's say you're working for a company and you have a project going on. You can use that as a theme. If you're not working, and if you don't have you can make one up. It could be a fictitious company, or you can pick a company that you know, or it's your choice. You have the freedom to selecting it. And depending upon what you pick, you might make it harder or easier for yourself. So think about something that, a company at least you understand, or a concept that you understand. So you're going to pick a project that is currently being worked on and come up with a fictitious project theme to work on if you don't have one. The plan should cover all of the phases of the project. You don't have to come up with a project plan. You don't have to say anything about the project outside of a brief description of what it's doing. Which is part number 1. So you're going to address financial, managerial, and technical issues. And so you're probably thinking, I don't know anything about financial issues. You don't have to. If you don't know anything about the financial aspect of the project, don't worry about it. But some things might necessarily be budget associated, might have certain resources that you might have to associate with you to work with or something. Depends on the project. So your risk assessment management plan, and it's called a management plan, note, risk management plan, because we're dealing about the management of these particular risks above and beyond the identification of them. This is kind of deceiving. It says 3 parts, but there's really 4 numbers. So don't let that confuse you either. If you skip the brief description, there's 3 parts, I guess. So number 1, you're going to describe the project. That's pretty easy. And you might notice if you go through this entire document here, you won't see a page length. There's no word count, there's no page length. Because here's what's going to happen. You're going to take a couple of different approaches on it. Some people, in fact, what I would do if I were given this assignment, I'd write a big old chart. And that's going to be 1 page, or maybe 2 pages. I'd probably do it in landscape mode, and I would actually kind of just put together a chart and visually, because it's easier for me to show it graphically, like in a chart, with columns, and I'll show you some examples in a few minutes of how to do it, than it is to write this out like an essay. But if you don't want to do the chart, you can write it out as an essay. If you write it out as an essay, you're going to get more words. It's going to be a longer paper. There's no minimum, there's no maximum, there's no spec on how long to make this. You just give me your plan, however you want to present your plan. You don't have to use a template. You don't have to use a plan, risk management plan format. If you go on the internet, you'll see a ton of them. They look like they look like requirements documents sometimes. It has descriptions, and some of them are like 30 pages long. You don't have to do that either. So make it less work for yourself. Because what we're looking at is only 10 risks. You're creating a list of your top 10 risks. So pick 10 significant risks. It doesn't necessarily have to be everything. If you did everything, you're going to end up with 60, 80, 90, 100 pages. Maybe even longer, depending upon how big. 10 is manageable, so hopefully. So you can identify 10 risks. That should be easy so far. After you picked a project, you described a project. You describe it in a paragraph. This project is doing X, Y, Z. Okay. So these should be placed in order with the highest risk first, and don't forget to describe how you rank them. You can put a little legend on the bottom. It says top 10 list, ordered, ranked of importance for critical completion on time. Or because the thing about a risk is that, and I think I did cover risks already. It was way back in the beginning. You guys don't remember that, but I think I may have talked about categories of risks, maybe. If not, I'm talking about now. So you have financial risk, completion risks, resources. Is it actually going to work? Is it technically feasible? Yeah, I think I do. I think about feasibility. In a way, maybe the second lecture or so. And, you're going to pick 10, but how do you know what category they're in? How do you know what criteria you picked them from? Your criteria might be, the first, most important item having to deal with finances or accounting. The next one might be resources. The next one might be time, availability. You run the risk of the project, running over time or something like that. So the point is, you're coming up with your own criteria for what makes it a top 10. You're coming up with your own list of your top 10, and you're hopefully giving me some kind of ranking information about what this is about, which may or may not necessarily be self-documenting when I see your risks. And I might, it's just basically a legend information that you could put on there. And so you are, for each one of the risks, this is why I say make a chart. So imagine, a box here, risk number 1 through 10, ordered in your critical. Number 1, what is the risk? So for each one of the risks, you're saying what the risk is. Risk. Main programmer might quit because we're not paying him enough or something. I don't know. Risk. The system, the algorithm might not work correctly, or the processing speed might be too slow, or the risk, somebody else is going to come to market first. So I should say the risk can be almost anything and in many different categories. So depending upon the category, the type of risk you've got, you're going to tell me what it is. Column number 2 might be a mitigating strategy for the risk. What you might do to mitigate. A mitigating meaning, if this risk happens, what are we going to do? Plan B. So if programmer number 1, head programmer, fails to complete the job, we're going to have programmer number 2 who's silently working on it at the same time. Simultaneously in the background. We secretly have another programmer working on this, just in case the first programmer fails, so we have the second guy. That would be a mitigating way of, how many people are going to, probably no one's going to hire another guy in the background to work on it. Instead, you're going to have some rabbit someone's going to pull out of their hat or something like this. This is what we're going to do, just in case this happens. We're going to have this trick that we're going to do. The contingency plan for the risk. So the mitigating strategy is, how are you going to mitigate, how are you going to lower the likelihood of this particular risk happening? If you have another guy working on it simultaneously in the background, you've got no more risk, essentially. You've mitigated it. Your contingency plan is, okay, this has happened. Plan B is the contingency plan. It's, now what are we going to do? Our contingency plan is we start over again with another programmer. If the first guy fails and the mitigating strategy doesn't work, then we go to the contingency plan. Kind of think of it sort of like a funnel where you're going through till you're going to hit rock bottom eventually. You're going to go through all the different points. And then after the contingency plan, the last one is how will you know when to invoke the contingency plan? Some trigger point. So you have to have some way of measuring the risk, because you're going to need to know when the risk happens, and when you're monitoring it, how close are you getting to the risk? Maybe you should start looking in the want ads for this secondary programmer that you need to hire. So you could put it out in columns. You could write it out like, risk number 1. Here's my, and then 1, 2, 3, 4. Risk number 2. Well, 1, 2, 3, 4. Risk might be easier, actually. It depends on how you think. I think like in the form of a chart, but you guys might think differently. You might think, number 1, number 2, number 3, number 4, and then list all those items for each one of the risks, which is what essentially you're doing. And then the next part of it is just more information for you. You want to include a description of the process you will use for managing risks. So this could actually be sort of an introduction if you wanted to. This could be a description for each one. I personally wouldn't do that. If I were doing the chart of all the risks, all this stuff would be on the bottom or the top of the chart, and it would be summary information about the chart. It would be like, okay, so this is how, this is the process that we're going to use for managing the risk. Every day, we're going to have to check in. Or at each phase of the development, they're going to check it off and sign it off so that managers have approved all of the changes that have occurred. And we're going to keep it online. We're going to have a website, that automatically posts updates about everything that's going on and the status of all of these little pieces in the project or something. And you can make up stuff. But what you're doing is you're kind of troubleshooting and you're thinking about the process that you're going to do to manage it. Relatively brief, less than 1 page of text. So keep it short, because you know what you can do on this? You can write a novel, actually. In fact, this is not a bad question for the midterm or something, or for the CSLO, because you can get way carried away with this. In fact, keep it short. Okay, for example, how will you develop a team? how will the development team monitor the risk? You don't have to answer all these questions. This is just to give you some ideas. What process will you use in deciding when to invoke the contingency plan? How will you handle emergencies? Will individual members of the team be authorized to carry out parts of the risk management strategy, or is it just one guy who's going to be working on it? So how often will you update your list of top 10 risks? Which might be an issue, you know. It was a risk today, but maybe it's not a risk tomorrow. Maybe that phase is already over with, and you don't need to keep it in your plan. You can keep monitoring for something that's already finished, you know. So maybe you want to, you know, have something scroll off a list or something. And then in part number 4, the last part of it, to help you manage the risk, you need to take regular measurements of the status of the project, which is kind of a sub-part of how you're going to monitoring it. How are you going to monitor it? You're going to probably do status updates. So choose a suitable set of project metrics. And most of you are sitting here going, what do you mean by that? Well, go back to the Software Engineering 1 notes. Look up the word metrics, measurements, and all the Software Engineering 1 notes, and you'll find tons of examples. Don't have to give me formal metrics. You don't have to go through a book or go online and give me, we're going to use the cyclical approach, or we're going to use the bubble approach. I don't need to know the scientific approach or the measurement or the metrics. The concept is, how are you going to do it in terms of what approach are you going to take? And choose a suitable set of project metrics that you will collect during your project to help you monitor the risk. And then describe 5 of these metrics in detail. Doing 5, this is really not that much work. So, for example, you want to know bugs, let's say. Let's say you're all the way done with the RS event, and you're going to do metrics. You're at the testing phase. So you're testing everything. You might have a metric that shows you the number of bugs found in this particular module. And you might say, well, as a risk assessment strategy, we're going to put all the modules out there and say the one with the highest number of bugs should get the most attention, maybe. Because what is that metric? What's that rule that says, you know, the most number of bugs happen in the smallest number of modules or whatever? Thinking that if you attack the one with the most problems, that maybe it'll have a dominoes effect maybe on the other one. I don't know. You describe your strategy, describe your metrics, and you say, well, I'm going to keep track of, you know, the number of bugs. What is it going to tell me? It's going to tell me that how close I am to having something relatively acceptable that is free of bugs, hopefully. Whether it is a measure of your product or a measure of the development process, well, I'm measuring my product. That would be a measurement that's associated with what I'm building. It's the end product. You could measure, see how many man hours have the programmers been working on it. You can say, well, if our programmers have been in here every day of the week and they've put in 60, 70 hours a week, and we're not even halfway done yet, and we thought this thing was going to be done in a week, that might be a good measurement of, in terms of the second here, it's a measurement of the development process. Oh, something's wrong in the development. Either we're not communicating well, our programmers are distracted by something else, we don't have good programmers, something is going on, we're way off schedule. The next one, how frequently you plan to collect the data. We're going to check on these guys every hour. Are we going to, once a week, see how many bugs we have left in the system? Or are we going to do it like every month? Or, you know, what kind of schedule are you going to put it on? How much effort you think it will take to collect in minutes per week? Like, you know, is this like an hour meeting that we have to do with all these programmers to see where they're at? Or can they just write a quick note, send an email message out? How are we going to collect it? How long is it going to take for them? Whether the method for making the measurement is subjective or some sort of an equation, some sort of logical accumulation of data that we're applying some algorithm to come out with some statistic or something, you know, which is kind of judgmental or not judgmental, it's calculated. And whether the scale used in the metrics is normal, ordinal, interval, or ratio, you know, is it a good, a fair? Is it a number between 1 and 10? What kind of scale? This question here is asking you what the scale is all about. Is the scale good, bad? Continue with the project, stop the project. And, you know, is it a ratio? We're 50% complete. We're 60% complete. We're 70%, you know, hopefully. I mean, this is not like the day before the assignment's due or something, or the project is due, and we're 60%. I would say your risk of failure is pretty close. So this fourth part is unrelated to your risk, really. This last part here is a separate kind of part that you're putting together that is an exercise in metrics, essentially, an exercise in the way you're monitoring. So there's really like maybe 3 parts to this assignment. There's the plan, which is kind of like number 1 and number 2. Then we have number 3, which is kind of a description of how you're going to monitor the process for managing the risks, monitoring the risk. And then the fourth part, or the last part I should say, is a list. And what you've got here is you need to put together, for each one of the 5 metrics you put together, give me something. So you can go metric 1, metric 2, or you can again put another chart down there. So you can have and you can put them in any order you want. You can put your description of your monitoring first if you want. Your chart number 1 gives you the risk assessment plan. Your chart number 2 going through your 5 metrics and all the information I've asked about that. And all the information is not like a novel. It's like 1 or 2 sentences for each one. Yeah. Tell me what unit of measure you're using. Well, it's going to be in inches. Well, it's going to be in lines of code. It's going to be a percentage, which is kind of easy. It just answer essentially or provide the information in a short description for each one of the 5 metrics. And essentially what we're doing is putting together all of the kind of forethought activity that would actually go into the development of a full plan without actually developing a full plan. So there's no required risk assessment management plan format, which ends up happening when you go online and you'll see what these finished products actually look like. And they're 60, 70 pages long. They have everything in them. And they're formatted with a table of contents. And don't need any of that stuff. Don't put together a risk assessment plan like a traditional development plan. Did I answer all of your questions?
Yeah, but it's quite hard.
Hard? This is a graduate course. It's not hard. It's only hard if you make it hard. If you think everything's easy, it's easy, right? Okay, please. Yeah, please send me an email message if you have a doubt in it. So, any other questions about it? When does it due? End of the term. When do you want to do it? Now-ish. Probably should be working on it now-ish. I've actually covered everything. Reliability, dependability. You can actually pull out of all that stuff. In fact, I think there was a risk lecture prior to all that, but this is several weeks ago. I don't even remember myself at this point. Right in the beginning of the course, I talked about risks. And maybe it was the business aspect of software engineering or something. I don't know. It was right in the beginning. So, but and then also the software engineering notes from the first course may also be beneficial for you on that. So, if there aren't any questions, we're going to move right along to today's featured presentation on the topic of testing. We have 2 lectures on testing. This is the first one, and I kind of queried the class. You guys want to see this one, or he wanted to see this one instead of the other one. So we're going to go in order. So if you've already had testing, what I'm going to try to do is kind of relate this at a higher level of abstraction. I'm not going to go through this is what you do to test a piece of software, because that's going to bore you to death. So, or bore you, I should say. Hopefully not to death. But, wow. All right. So what are we looking at? We're looking at a presentation tool that's not working. Hold on 1 second. Let me fix the technology. Now we have technology that's working. All right, so we have the testing process. So in Software Engineering 1, we put together a test plan, and we did that in the requirements. What are we doing in the requirements? We did it in the design document. You could put test criteria in the requirements. If you're working on a mission-critical type of application, let's say it's an airline scheduler. No, heart monitor. That's a better one. I just said the word death earlier, so I'm thinking about hearts now. If we put together a software application that's going to be put on a chip that's going to be put in somebody's heart to help it pump or something, we're going to have it work. And so in the requirement specification, we might put a requirement for reliability, for dependability. The thing's got to work. And if it doesn't work, it's got to reboot itself. and start working again, which would make it more dependable. And we could put down their testing requirements in such that it must be 99% reliable, which means we'd actually have to show at the end when we delivered this thing that we can prove that it's 99% error-free, or 98%, whatever number we put on there. And we're going to say 100% because it never comes out 100%. We all know that. In fact, if you walk away with anything, that's what you're going to walk away with, because I keep saying that over and over again. Nothing's ever 100%. But with that notion in mind, the testing process is designed to get us to that 98% or 99%. And it comes in different sizes and forms. In the requirements, we can actually put it together and we can say, this is what we need to do. These are the major components that we want to test that have to come out with provable scores. And we can actually build that in there, which requires us to actually go through it in terms of our contract that we have signed with the client. But we don't necessarily start thinking about it really in terms of the implementation of the process until the analysis and the design. So in your Software Engineering 1 class, when we went through the different stages of the development process, after we got done with the analysis, in the design doc, we put together like, 10 test cases or something if you took that class. And it was test cases. And it was only one form. It was black box testing, actually. And it was only one form, which was kind of minimal, not very much. So in this class, what I want to do is kind of give you a better overview of what kinds of testing, what process actually needs to be done in a real-world environment to actually make this efficient. Because all the testing in the world on black box isn't going to tell you anything about any other characteristic outside of the functionality of the system. From an outside looking in perspective, it's not going to catch all the errors. Unit testing isn't going to catch all the errors either. Automated white box testing, not going to catch all the errors either. We have to just kind of put together a package of all of these different techniques together in a plan or a strategy or process that's going to actually go through, and that's going to be a little bit better. That's going to give you 98, 99% reliability. So in terms of the testing process, we can go through unit, system, acceptance, and major parts, hopefully, while we're going through the process. And as I mentioned, Software Engineering 1, we build the testing kind of development at the same time as we're building the software. They're both running together, hopefully. And we have different types of tests that we can run at each one of the different stages as we go through. What we're looking at is time. It requires time on the schedule. And so this is a problem. Everyone waits till the last minute. Oh, you can always do the testing last. And then nothing ever stops at the right time, so the testing never gets done, long story short. Or the testing is an afterthought. Or the testing is too time consuming, so it gets cut short. Or we started the testing too late. We didn't start it early enough. So it may require substantial investment in test data as well. Equipment and testing software, which nobody ever thinks about either. So when they go to budget out the software that they're going to build, they think about all the tools they need to build the software. Nobody ever thinks about anything that they need to actually test the software with. So in terms of software engineering, if you start out with a test plan, at the same time as you start out with your build, with your design document, hopefully some of these typical problems are going to go away and you're actually going to do a better job. So this is kind of like an art and a science. Like software is an art and a science to begin with. And there's no one way of doing something correctly. It's the combination. So long story short, it has to be planned just like the development. So good testing requires good people as well. So you don't want the engineers, and you say good people, yeah, I'm going to have my head programmer test this. Wrong. You want testing people. You don't want the developers testing their own work. It's like the wrong way of doing it. You also need documentation that includes management and client reports and are important parts of the testing. So, and also the definition of what is done, which is kind of an interesting question because a lot of software is not done before it's produced. It's out in production. It's not done until it's at some level of expected reliability or dependability or whatever metrics you put on it, which nobody puts on it. Because why? You see, if you don't put an expectation on it, then you can never exceed it or you can never go underneath it. It's just, you're never going to worry about the expectation if you don't have one. So if the software works or does it not work is usually the criteria for when it's done. But we all know software does, whether it works or not, it's not really the question. It's how well does it work? How long does it work? So we have a test design. So we design this so testing can never prove that a system is correct. That's a good thing to remember. It can only show that a system is correct in a special case, and that it has a fault or does not have a fault. And it's okay for the system to have a fault, as long as the fault's not a critical fault and it's something that's acceptable, then it's releasable at that point. So huge decisions, in fact, managers like sit around and go, should we release it? Is it ready? And they always ask the programmer, is it ready? Like you're going to know? Like you did your part, but nobody else did their part. So yeah, it's ready from my perspective. If I wrote it, it's done. But, they just sit there going back and forth, and no one really has the right answer to that. So the objective of testing is to find faults. We all know that. And testing is never comprehensive, and testing is expensive. And those are just the realities of what happens in terms of the design. So we have strategies. So we can apply these strategies, and the reason why testing is actually kind of thought about and built into the plan of the design is because you can design and test in the same format simultaneously in parallel, and then testing never becomes an afterthought. So a lot of like the JUnit stuff, a lot of the automated testing tools that work with the source code development can actually happen at the same time simultaneously, and everything can kind of flow together smoothly until the software is actually finished. So in terms of the strategy, we have the bottom-up, top-down, and then stress testing as a strategy. And it depends on the type of application as to whether or not it makes more effective use. Because a lot of people say, oh, we always do bottom-up, we always do top-down. And then whether or not, one might actually work out better for different development environments than another, also product-related. So in a bottom-up, we have each unit is tested with its own test environment, which means if we're going bottom-up, we're not using the rest of the application to test it in. We're doing unit by unit in a separate outside, you might want to call it artificial environment. That's not necessarily the environment that's part of the rest of the program. In the top-down, we have the large components that are tested with dummy stubs. So we test the environment. So in a top-down, we're actually testing the operating environment of the program, and we're putting in artificial units that aren't quite ready yet. So one of them is going to be testing the units a little bit better. The bottom-up is going to be testing the individual units. In a fake environment, the top-down is going to be testing the environment with dummies units. So your units aren't going to get... So you probably want to do a combination, actually. So you take one through, and you go back and you do the units individually. So that's a strategy, but it's time-consuming. So in the top-down, we're looking at the user interfaces, the workflow, the client, the management, demonstrations. So you could do it top-down, which is actually kind of common, and then do an individual unit to unit. Because what ends up happening when you do the top-down, you're going to find bugs. You're going to find faults in the system. You're going to say, well, it's with the printing functions of the reports. And then you go pull the report object out of there, take that unit over here and test in a totally different environment. Oh, it doesn't fail. Oh, it works just fine. Okay, so you put it back in and you pull another component out of it and you go, oh, this one fails. Well, that's a weird effect. This one's having an effect on that one. Rarely is like the unit you think is going wrong is actually the one that's really going wrong. Sometimes it's something else that's related to it, the interfaces with it, that's not giving it the right information, or it's losing a connection or something. After we're satisfied that everything is actually working and that we have all the functionality implemented, and left hand is talking to the right hand, and could you please keep it down in the back? Is this hard for me to yell over you? I'm sorry. All right, after we're sure that we have everything working, we can take a stress test kind of approach as well, where we're testing it beyond its limits. We're pulling out, what if we put all this data in all at one time? What if we try and run all the reports simultaneously? What if we overload the system? And that's basically going to tell us how strong the system is in terms of its error handling, its error protection. Giving it bad data, giving it too much data, the wrong data, would actually be considered a stress test kind of environment. Where we have real-time systems, transaction processing systems, where we might not necessarily want to figure these problems out when it's put in production. We'd like to know that after 10 people have used the shopping cart, that the shopping cart crashes. because the log file gets too big and it's too long for it to load and it messes something up. So that testing is going to be different. In fact, it's going to give us different results. In fact, all three of these different strategies are going to give us different results. So it's not one to say, one is better than the other. It's a combination that you pick. And we have closed box, open box kind of testing. Closed box testing is carried out by people who do not know the internals. Black box, closed box, kind of same concept. You're not testing the functionality, you're testing the interface of the functionality, one module to another. Open box, another terminology, test is carried out by people who know the internals of what they are actually testing. It's kind of similar in terms of what it is you're looking for. Are you looking for an internal error? Are you looking for something that can be caught out by major functionality? We have in the testing world, if you take a testing, actually there's testing tools and something or other going on right now. You got white box, black box, glass box, blue box, red box, all these boxes. There's nothing more than different approaches. Also, you might also consider who's doing the testing. You can actually have different types of groups of users test who are going to give you different results as well. Regardless of what blue or red box they're testing, it's going to be a slightly different environment, which is what you want. So the trick to it all is variety in terms of what you're doing in your approach. So what is the advantage of each approach? You can probably come out with your own, actually, in each case. And how do you set about testing test cases? How do you set? I don't know. Maybe it's how you go about selecting test cases. Which is also another kind of thought to keep in mind is what test data are you using and what test cases have you come up with? I can come up with a lot of different ways of testing functionality on a system. And then we always talk about coverage in testing classes, What percentage coverage do you have? Are you testing only this unit or only that, or are you testing the entire application in terms of its coverage? And there's coverage strategies as well, which you learn in testing classes. What kind of coverage do you have? What percentage of the coverage is most important on this aspect versus that aspect? So you can actually put priorities on the coverage. So some of these testing tools, especially the automated ones, will give you statistics. We'll say, 40% of your bugs are in this one little section or something, which helps you because then you can take that section out and kind of, let's see what's wrong with it and kind of debug it again. So after we've gone through and we've figured out what kinds of testing do we want to do? Do we want to do open, closed box, black, white, whatever, kind of unit testing, system testing? Then we have stages. And so we can actually organize the methods in the stages so it makes appropriate use. And again, this is kind of a management science, actually, / technical science, because depending on what you're doing in each stage, it might be more effective managerially to test all the units first, maybe test the integration last, maybe, typically. So testing is most effective if divided into two stages, in which we have unit testing and system testing, and then we have acceptance testing. What we don't want to do is just acceptance testing or unit testing, we need to do all three, essentially. And in terms of unit testing, that's usually done first because it's easier. Somebody writes a piece of code, writes a mod. We finished the reporting tool. Okay. Well, the reporting tool is done. As a unit, you can take that over and test it while something else is being written before you put it all together in terms of the overall system testing. Whether you're doing top-down or bottom-up, you can essentially apply each one of the methods when it's appropriate. In terms of the system testing, we have integration, function, performance, installation. That list is just a list. You can actually come up with more, actually. More items that you can probably put in there in terms of whatever it is you're building. If you're making an Android app, you're probably going to put in there connectivity, connection testing, maybe. I don't know if it's using the GPS, maybe the GPS tools, whether they're integrating correctly or something, or mapping or something. In terms of unit testing, what I'm going to do is not give you a complete overview of every one of these different testing methods. Well, I am actually, but I'm not going to give you a lot of details. This is what you take a testing class for. In fact, an advanced testing course would hopefully have you put together testing plans and actually test software, hopefully. Basically, a little above and beyond a basic testing understanding. But in order to do unit testing, what we're talking about is testing all the small pieces, the single classes. Unit testing, that's with JUnit. That's why they call it J for Java, unit. You're testing class by class. If you're not familiar with that and you have an interest in it, go online, look up JUnit. Very popular, actually. It works and it's written in Java. It works along with Java. It does unit testing. Probably one of the most popular programs out here. Integrates with Eclipse, which is why I like Eclipse, actually. And if you were in my Android class, or if you want to have an interest in it, you go through the Android notes, you'll see each one of the apps, there's a JUnit app that's written along with it. It's a lot of effort. In order to do that type of testing, you have to have a lot of programmer time. You can't have one guy doing both the testing and writing the code. It's too redundant and it's too time consuming. So people who are real serious about it have testing programmers, and they have the real programmers because these guys have to focus on getting the job done. The testing guys, they're focusing on writing the JUnit tests and creating the unit environment. And why are they going to do that? You write it once, and you test it forever. So if the program's going to make it, hopefully through a couple of different releases, you don't have to go back and duplicate the effort, especially if you're following an object. If you're taking my object-oriented design course, then you're building a hierarchy of classes. Once you've got a class created, and you have a JUnit test to go along with that class, you leave it alone. You just call up, when you want to test that class, you call the unit test that's already created for it, you run that. And it kind of all works together, hopefully, in terms of your object-oriented design, as well as your unit testing that's integrated in while your development's happening. So it's working simultaneously. If you wait until you're all done and go, I think we need some JUnit testing done, too late. You're going back and you're reinventing the wheel. It's easy. You can do it. It's not impossible. But it's time-consuming, and sometimes it's hard for the unit tester to actually kind of see the big picture when it's all together versus in the smaller pieces. So it's a lot better if it's done simultaneously with the development, if you're going to take that approach. If you're not using Java, you can't do that, essentially. You have to use, a C++ unit testing tool, for which there are some on the market. They're not very popular, and they're usually paid-for tools. JUnit is open source, so it's free, which is why it's popular in some ways, which is why Java is popular, actually, as well. Not the only reason why, but one of the selling points. Okay, so the emphasis is on the accuracy of the actual code. You're testing the code itself. So it's a white box or open box, if you want to call it that. The test data is chosen by the developer based on the understanding of the specifications of the known units of the test, the knowledge. So the programmer is deciding this, which is why you have the unit test writer working with the programmer. And they're actually kind of helping each other. Sometimes they can actually work as a team and do both together, which is good. Sometimes, depending upon the budget, it's the same person doing both, and you're just required to do it at the same time. Can be various different levels of granularity to it. You can test each one of the individual methods, each one of the data members. You can test the whole thing. You can test that class and that class working together. Many different ways of testing it. Open box by the developer of the unit. So if, what does this blue thing say on the bottom? If unit testing is not thorough, system testing becomes almost impossible. Actually, it does. If you are working on a project that is behind schedule, do not rush the unit testing. Actually, that's a common problem. They don't test the units. They put it together in the system, and then it's like, well, what unit's causing the problem? Well, we only have all these tested. We know it's not over here. Is it over here? And then we find out, oh, it is over here. Because it's almost like starting and trying to build a house with beams that you're putting together, and the beams haven't been stress tested to know that they can support weight. So you don't know what beam broke, but something broke. But because you never even looked at the parts you're using on it. So you're assembling parts together. It's nice to know that your parts were not defective before you put the whole thing together. And then when you put the whole thing together, you realize, oh, there's a problem. Well, what part is it? I don't know. We didn't test the parts. So testing the system and the subsystem. This is another common problem people have. They put the thing together, they roll it out, it's on the network, go for it. And then when I upload assignment, this is a really bad example, I know. I'm uploading assignment to the ITU EMS and I get an authorization error. I'm not authorized to, people are getting this actually. It's going on right now, and if I don't mean to insult anybody if you are working with the ITU EMS system. However, I know you're smiling over there. No insult to the developers, because it's actually something that happens all the time. Did they test the system, the subsystem, or have they tested the entire system put together? My suspicion is that they may have tested the subsystem, but they didn't test the entire system as it was put together in the main unit that the interface is running through. Meaning your EMS student account perhaps might not have the right authorization to access some other part of the system that needs to be authenticated in order for you to actually not get that error message or something. Which tells me that perhaps there might have been some rushing, which there probably was, in terms of getting something rolled out, which happens a lot. You test it, application, you test the database is working great, the front end, the shopping cart's working great, the inventory thing is working great. You put it all together, you slap it all together, and you roll it out the door. But you never tested the big picture. So you don't know that when this happens, every 5th shopping cart element gets dropped off the list because the inventory is too small. Because each one of the subcomponents might actually be working perfectly fine on their own, but when you put them all together, then you got to work with, who's got access to what authorizations are going on, what information is getting lost between point A and point B, what's being translated incorrectly, what didn't quite line up correctly. So sometimes when networks are involved, you've got connectivity that might be causing the problem, bandwidth issues that are causing the problem, all sorts of different things, access rights to certain directories on the network that might be causing the problem. I suspect it has something, the EMS issue probably has something to do, and it probably is already fixed, by the way, I don't know. But it may actually have to do with some sort of authentication issue that wasn't thought about before. It may have been the time in which your account was created, or something, some policy was set differently for certain user accounts than others, because not everybody's having that problem. So, anyway, long story short, system testing and subsystem testing. So test on the components or the complete system, combining units together that have already been thoroughly tested. Emphasis on the integration and the interfaces. So you can do this with dummy modules, actually. In fact, you can test the units as they're integrated before they're actually integrated. But that's a lot of work and sometimes impossible to do, especially if you're working in a real-time environment. It's real hard to test an ATM software without actually hooking it up so that it runs on a network so that it can communicate with the star system or the whatever system it has to communicate with, which you may not necessarily have the luxury of being able to have access to without a real running application. Or it might be expensive. In fact, a lot of shopping cart, credit card processing systems, you got to run it for $1 through 20 times, and then the system, it's a hassle, it's time consuming, it's effort, which is why it's not normally done. It's usually too hard. How am I going to test that? Oh, we'll just put it up. The first customer who comes in is going to test it. We'll use their card number. We'll see what happens. It happens, actually. You can use trial data that is typical of the actual data and or stresses the boundaries of the systems for failures, for restarts. But all the data in the world that you test it with is test data. Until you actually get the real data, you don't know exactly what's going to happen. So it's very common for there to be unknown problems, even in systems that are thoroughly tested with a lot of data. So you can carry out systematically adding components until the entire system is assembled. Once you've verified that this works, that works, that works. And actually the kind of cool thing is if you can get part of it up and running and integrated, like the database, and already processing things, from that point forward it gets easy, because you already know that's working fine. And then you'll load the next piece in, which is kind of like how modular software is easier to work with from all aspects. It's easier to change components, but it's also easier to test and easier to upgrade. Open and closed box by development teams or a special tester team. Normally what ends up happening is you get testing people, usually in the old days it used to be interns or college students on summer break who come in and do testing. And they run a bunch of test cases, they have all this data that they put in. Now we have real users out in the field to do the testing, or customers that do the testing for us. So we put the product out there and the customer calls in and says, you know what, it's doing this really weird thing. And you go, oh, hold on, and they think, oh my God, we forgot to turn that error message off. Okay, or we forgot to turn that debugging thing off, which just sometimes happens. So this little blue thing says, system testing is finished fastest if each component is completely debugged before assembling the next. Yep, it is. Acceptance testing. This is the easy part. Here it is. Do you want it? Is it okay? Sure. I'll take it. It's the client saying, okay, the only problem is sometimes, let's say, going back to the example in the beginning, you're building software for a heart monitor. Clients going to want to know before they accept it that, I mean, I certainly would want to know. I hope these days I never need a heart monitor. However, if I ever did, I'd want peace of mind before I accepted it that it's going to be 99% reliable. Although I would like them to tell me it's 100% reliable. I don't think they're going to do that. However, I want to know that there's a backup plan. I want to know that the system's got an automatic restart function to it, or it's got a this, or it's got a that. All the features that might be associated with it, they need to be demonstrated to me. It's kind of like how we do anything. Like, you know, oh, here's how we can fix your computer. This is what the program does. So you show it to the customer, and they go, oh, yeah, looks good. Depending upon the criticality of it, you might need to see some statistics. Look, it's kind of like how people used to buy furniture from IKEA in the old days. I don't know if you guys remember that, but they had the chair, and they had the thing sitting on the chair, like 2,000 times in the closed test environment. Look, somebody sat on that chair 10,000 times, and it didn't break. Or they used to do this like with test dummies. You know, they put the dummy in the car. Look, the dummy went 200 miles per hour into a brick wall and only suffered a concussion. Oh, great. You know, I'll take that car because I'm going to go 200,000 miles into a wall too. So I just want to make sure I'm going to be okay. Acceptance, that's acceptance testing, actually. That's, are you able to buy it? The entire system is tested as a whole. We don't normally take out the pieces of the car. We just take the whole car, ram it into the wall. The emphasis on whether or not the system meets the requirements. And does it have enough safety for me? Is it going to, can I trust it? Uses real data in a realistic situation with actual users, or dummies, depending upon how safe we are. In fact, I'd like to see someone put their car through a test with live people in it. That would impress me, actually. In fact, you know, when I first got my smart car, I watched a YouTube video. They had a monster truck and a smart car did a head-on collision because safety was an issue. You know, and people look at that car, they go, "Do you feel safe in that car?" I go, "Yeah, because I watched the YouTube video. Here's what happened." Monster truck and smart car had a head-on collision in the middle of a yard. And the monster truck ended up losing control because the little smart car hit the tire, hit the rubber tire. It bounced off like a pinball, and it rolled. It rolled like a couple of feet. The monster car, the steering, it ruined it. It dented in the steering axle thing or whatever. So if I ever hit a monster car, I know, hold on, because I'm going to be rolling all over the place like a ping pong ball, whatever, a pinball. And anyway, so then I looked at the car and went, wow, it has roll bar, built-in roll bar suspension. So what they put in the car was airbags all over the place and roll bar suspension, with the assumption that if it ever hits something, it's going to bounce back and roll all over the place. So the car's meant for rolling, actually, which is interesting. Because what if I take my smart car and go a head-on collision with a brick wall, which they actually had on YouTube, and unfortunately the passenger, the dummy died. So it's not a reliable car, actually. Long story short, it's nice if you want to go on an amusement park ride and roll around upside down and roll all over the street if you hit a big truck. But if you hit dead on and it's a solid, not rubber, depending upon the composition of the material, you go right into it. You go flat. So anyway, I'm not planning on any of those things. I will be seeing you next week. Hopefully. But no, I mean, it's part of acceptance. And as a consumer, the reason why this example is actually good, I still bought the car. But I don't really drive it on the freeway that much. And I don't like to drive it in the rain. And, you know, I accepted it with the assumption that it's not a safe car. So we accept software with the assumption that it's going to make some rounding errors. We're not going to put all of our data in there, maybe. Or we use programs. We download stuff on the internet all the time, programs, and we accept it. Oh, yeah, it's good. I like it. It serves its purpose. But we know sometimes it makes errors. Sometimes it doesn't work right. Even people use computers like this. People loved Windows Vista. There was actually people who loved Windows Vista. even though it ran slowly or crashed or had this problem, they liked it for something, right? But they used it, it was acceptable because they only paid $200 for the computer or something, or, you know, it was cheap or something. There was something about it that they accepted. Long story short, we have variants of acceptance testing. What I've been talking about is full product, end product. Here you go, we're going to deliver it, we're going to give it to you. We have alpha, beta, you know, it kind of sounds like a sorority house here or something, alpha, beta, mega, whatever. And parallel testing. So in the alpha, and we're all familiar with beta because we all use that right now. Everything you download, everything you install is really a beta copy because end users are doing a lot of testing. And all your Gmail versions that you've used is all beta software. It's not quite done yet. It's still in the makings. It's still being, features are still being added to it. And in the traditional beta, and I'm starting with beta because that's more popular, it's a word a lot of people have heard of or are familiar with, clients operate the system in a carefully monitored production environment. In the old days, you did. In the old days, you signed up to be a beta tester. You downloaded something, you used something on the internet. You had to tell the people that you're using, that you got it from. You had to sign up to be a beta tester. You gave them, here's my operating system, here's everything else I'm running, this is what I'm using the program for, blah, blah, blah. Like the old Netscape browsers. Some of the earlier Windows versions were delivered this way. And nowadays they don't do that. They still give you beta software. In fact, Windows 7, no, Internet Explorer version 7 or 8 or something, give me an option. Would you like to try the beta version? And in exchange for getting the software that's not quite available yet, because it hasn't been fully tested yet, because you're doing the testing, in exchange for that, you're going to hopefully give them your feedback, maybe. Tell them what happened, what went wrong. Because basically it's a testing mechanism for acceptance testing. It's close, but it's not quite ready yet. It still has issues. We haven't quite know how these features are going to work yet. So we're putting it out in beta, which was the concept. Now everything, there's a lot of software that we're using like Gmail constantly in beta. I don't think Gmail's done yet. It's beta. And some web browsers, Firefox, all these Thunderbird browsers and things, or email clients, they're really just beta versions, actually. New features are being added and added. And the thing is continuously being tested. Alpha, the client operates the system in a realistic but non-production environment. Alpha is before it gets shipped out. Only developers, only the project team is looking at the alpha. End users are looking at the beta. So that's how that works. Parallel testing, the clients operate the new system alongside of the old system. Makes it easier with the same test data, with the same data, and then they compare results between the two systems. This is how you know that the new system is working without actually having to rely upon it 100%. So you still got the other system running. Only problem with parallel testing, and people go, oh, why don't we just do that? Late adoption issues. When an employee walks in on Monday morning and they find a brand new system on their desk or a brand new program on their computer, they're forced to use it. So they're immediately translated and they're immediately put into that new system automatically. When you have it running in parallel, there'll be people called late adopters who will never touch it, who will never use it. It'll sit there forever until they're forced to use it. And then they go, oh, well, the new one's going away next month. You better start using it. So you don't actually have everybody using it, so you don't actually know if there's going to be problems with it. Until you get everybody on it, everybody using it 100%, you have no idea to really even fully integrate it into the company environment, fully test it. It might not actually have a feature that somebody uses it for that's missing or something of that nature. Also, with parallel testing, you have two sets of data. You have everybody, all the early adopters who've picked up and started using the new system, and you also have the other people who have refused to change anything and are using the old system. You have two sets of data. Someone has to manually put it together, and at the end of the day, there's too much work in terms of putting everything together. So, it's personally easier to do what's called a direct cutover. Just pull out the old software, put the new one in, and then hope that it works. Pray that it works. With the concept of test cases, this is the only thing we really actually looked at in Software Engineering 1 was the concept of creating these test cases. And a test case, by definition, are specific tests that are chosen because they are likely to find faults, hopefully. What you don't want to do is put together a bunch of test cases that don't find anything. It's useless. It's not really testing anything. People who get paid by the hour to put together test cases spend all day putting together hundreds and thousands of different test cases, and it's more like writing paperwork, which is very unproductive, actually. Because what ends up, in fact, what you want to do is pay them by bug. Pay for bug fixes, don't pay for test cases, because bug fixes are more important. Test cases are chosen to balance the experience against the chance of finding a serious fault, hopefully. So we have a case chosen by the development team, cases chosen by experienced outsiders and clients, cases chosen by inexperienced users. So in software engineering 1, what we looked at was the designer, the developer, who was actually creating the test cases. The project team was putting this together. In real life, what you would want to do is extend that, use the same concept, but get them from a variety of sources. Require that your users put together some test cases. So require, get all sorts of different kind of input, because people use the system in different ways. Not everyone's going to think of the same thing. And then we have this concept of coverage. So we have, in terms of the selection, we have the coverage of inputs that might actually exist. So the object is to test all of the classes of input, whether or not they're data, ranges of data, valid data, invalid data. Because it would be nice, in fact, this is what programmers do. They find a piece of data that's supposed to work, and they use the same piece of data over and over again. So this happens with passwords, actually. So, you're going to test it, you're going to run through it, you're going to use the same password, same username, and you're going to log in constantly using the same data to test with, thinking, well, it worked last time, it's going to work again, What ends up happening is, what happens if you put something invalid? What if you put a wrong password in, or what if you put a wrong username in, or something of that nature? That's really the art of the coverage of the inputs, is to figure out, variety, essentially, of the inputs, and then also the program. So the selection of the program, the objective is to test all the functions of the computer program itself, meaning the coverage, or all the features of what we're looking at. Paths through the computer program, that's another problem that actually people don't think about. They test the major ones, and then they go, well, what happens if this fails, this fails, this fails, and this fails? What actually happens? And then you end up having, this blue screen comes up. Do you really think Microsoft wanted a blue screen to appear on the screen? The blue screen never comes up anymore. But, in fact, it was something that came up by default for the desktop or something. In fact, it was a feature that was built in that actually kind of just came out of nowhere that ended up showing up on the screen. Now they fixed it so it doesn't show up at all, but that was actually kind of a weird phenomenon that occurred in the program, because one of the paths didn't go through correctly. It ran into a situation, it did some error checking, and all of a sudden things just collapsed. Things just went wrong. So program flow graphs, checking all of the every path, make sure it's executed at least once. And then we have dynamic program analyzers. This is where some automated testing tools might come in handy, actually, to simulate the working environment and exercise stress test all of the paths to make sure nothing falls through the cracks, that all of the scenarios work correctly and all the paths are reachable. Because sometimes we actually do have paths that are not reachable. In a finished product that's on the market, we have paths that don't ever get reached in terms of the execution. So what we can do is count the number of times each path is executed, highlight or color code the source code. You cannot use this in a time-critical software situation. It doesn't work, because it's too much work to actually go through and test all of the different paths and to document it correctly. So the testing strategies of the program, we can have a statement analysis, we can have a branch testing, and this gets into different types of internal or white box type of testing techniques, and these are all features above and beyond the unit testing concept. So this is the ability, how do you test every statement? So if every statement and every branch is tested in the program, is it correct? Do we have illegal statements? And usually what ends up happening is it's not a compiler error, because those are fixed. We have a bunch of legal statements in the program, but some of them the logic might be wrong. And I'm sure we've all run into that, where we've written a program that does something really unexpectedly. And we go, oh, because the range that we were checking for, we were one off or something. Or our loop went one extra time or something weird happened in terms of logic. And then we have a whole breed of statistical testing. which is interesting. You determine the operational profile of the software, you select or generate the profile of test data, and then you apply the test data to the system, record the failure patterns, and you have a bunch of statistics. You compute statistics, values for metrics under test conditions. So you can actually kind of use this kind of as a measurement in terms of your second assignment that I went over at the beginning. Some of these things I've been talking about in terms of testing is actually applied to some of the development process and some of the monitoring for risks. Because the more testing you do, the lower the risk, hopefully, the more reliability the software is going to be in terms of the program. If you're testing the development process, that's going to be a little bit different. Because you're going to have different types of measurements that you're going to come out with. But statistical analysis is actually kind of common these days because it's supposed to be, I consider it sort of like a junk science, but it's supposed to be accurate measurement of how reliable, how dependable, how bug-free your program actually is supposed to be. Some advantages to this is you can test every large number of very large number of transactions, come out with a number, essentially. And you can test extreme cases, loads, restarts, disruption. How many times does it restart? And every one of the failures, what percentage of it gives us this particular error message. Which is interesting because you have some programs that come out and you always see the same error message. Say one more time. Computing values or measurements in regards to a test condition. It's just like performance testing. You're performing routines on the software and you're coming out with what percentage error did you occur, what percentage of error occurred, or it might be what percentage of reliability, accuracy. It depends on what you're testing in terms of the nature of the program, the operating environment. It might be, how long does it take statistically to get a connection? In fact, that would be an interesting statistic to do. It's performance testing. Yeah, it's on the entire system, and you're putting a number on some characteristic that you're interested in putting a value on, and disadvantages of it might be uncertainty in the operational profile, unlikely inputs. If you fix the test environment, it's kind of like statistics in general. If your population group is all of the same nationality, the likelihood of something, or it depends on your data, your inputs, which is your inputs. It's expensive. It takes time. It's done differently than a lot of the other testing is done. So you can't sort of merge this in. You can kind of put it in with acceptance testing, I believe, a little bit. And some of these statistical testings are actually done on complexity. So we used to, you can do automatic, with C++ used to be a program, I can't remember what it was called right now, I'm having a mind blank, but you gave it your source code, it went through your paths, your loops, your if-thens, your cases and stuff, and it gave you a statistical number on how difficult. It's like cyclomatic testing or whatever. It took your program and branched it all out, and it told you, given the length of each one of the branches and the number of branches, how difficult that was going to be to test. And some programs would come out with a higher percentage of errors naturally, given the complexity of the code. So you're doing statistical analysis on the likelihood of you having more errors versus fewer errors. And it's on the complexity of the internal structure of the code. So there's different ways of programming, you guys all know. Different ways of designing loops, creating functions, not using functions. Given the number of functions, if the program had more versus another program that had less, it might be easier to test it. Actually, it's easier to test programs that have functions in it, that are using classes or using submodules. The likelihood of there being a problem is lower, naturally. It's just the nature of the design. So, what's about them? Expensive, can never prove high reliability. That's why I go back to statistics. A lot of people think it's junk science. Because you can get statistics to say practically almost anything. With a 98% with a likelihood with a 100% chance of error. Is whether or not your error, if you know statistics, all you have to do is weigh the error analysis of what percentage of error is expected. 50%, you might as well just flip a coin. You'll probably get a better accurate reading about what's going on. because the likelihood of there being an error is high in terms of what the statistics is actually telling you. So, not to put down statistics, I think it's very done in a controlled environment with really good data and properly. You can actually show. It's a way of verbally explaining phenomena that occur that you can actually kind of use as evidence for something to show data. So, but no one's going to rely on statistical analysis 100% for their software testing, I guarantee you on that one. So regression testing, another one. Regression testing is often overlooked and underutilized because people fix the problems and go, okay, put it back together, it's all done. And regression testing actually works with appliances too. So you fix an electrical problem, you run the whole thing, oh, it failed again. Oh, man, because it had more than just that problem, or that problem caused another problem. Or you fix this problem, now it's got too much electricity coming, it shorted out another thing or something. Or it happens with hardware, software, components, products, toys. What is it? Regression testing is one of the key techniques to software engineering, and bold and highlighted and big caps there. Applied to the model software to prove confidence that the modifications behave as intended and do not adversely affect other behavior of unmodified code. So people go, oh, I fixed the module. The module's working fantastic. You put the module back in, and it still doesn't work. It's kind of like probably what they do with the EMS. They made a few changes. Put it all back together. Why are we getting these errors? What happened? You know, it's because you didn't regression test it probably. You didn't test the change against the entire system once you put it all back together to see that it all worked properly. And in hardware software, they do what's called burn testing, or they do long-term stress testing, or which leave it running overnight to make sure that components like heat and electricity, things that over time don't cause an issue. In fact, software can be tested the same way too. Leave the operating system running for 12 hours or 15 hours or something, because we want to know that it doesn't, you know, the cache doesn't fill up and the whole thing dies, or, you know, the log file gets too big or something, because that kind of testing is actually kind of needed as well. And that's more stress testing than it is regression. Regression testing takes, you know, after you've taken it apart and fixed the small pieces, put it back together, test the big unit altogether. Basic technique is to treat the entire, repeat the entire testing process for every change that occurs, even the small ones. So just because you change one small one, go back through it. In fact, if you have automated testing put together, it's possible. Because what ends up happening is people don't do full regression testing. Nobody would. It's not practical to begin with. It's way too time consuming and expensive to do, because it delays your release. So if you fixed it, they usually do like a system or integration test on it. They don't actually go back through and test each one of the other modules that didn't change. Why would you do unit testing again? But theoretically, if you're following the proper standard, everything should be repeated. Everything right from the beginning, no matter how different it is, no matter, you know, how small the test was. So, in regression testing, we have the program testing, which is pretty much what I've been describing. Collecting a suite of test cases with each with expected behavior, creating scripts to run each one of the test cases and compare the expected behavior. Scripts may be automatic or have human interaction, actually. Hopefully you have it all automatic, because then you can just turn it on, it can test itself overnight, and hopefully it won't stop on each one of the failures. And then the next morning you come in and you go, oh look, these are the ones that failed. Well, now we have something to work on today. You know, go through and fix the ones that failed. So when a change is made, no matter how small, the bug is fixed, and then you add the new test code that illustrates the change. The test case that revealed the bug, as an example, might actually be something that you want to run again. So before releasing the change, you rerun the entire test suite. Actually, not just the test that failed originally. So the documentation of testing. Testing should be documented for thoroughness, visibility, and maintenance. So this is where people really run short. In fact, when you write a program for a class, do you actually write down formal test cases? No. In practice, the way we learned how to program, we didn't actually do any of this stuff. Instead, we just write the source code. And then we tested, it kind of worked. So sometimes people test as they write, or they wait till they're all done and they test it. And people have their own different little philosophy about how to actually do some internal white box testing of their own work. Nobody ever sits down and documents anything. In fact, it's really hard to get a programmer to actually put notes, self-document the source code, and label your variables and put notes in there to actually help whoever looks at it in the future, because there's this assumption that you're the only one that looks at it. So outside of that kind of thinking, when you do this for a living in a software development firm, there's a test plan. So you actually have to follow through the test plan. So while you're writing something, you made a small change, you actually have to go back through and, let's say, edit the header of the file that you changed, edit the package that it went with, edit the directory notes here, edit the document here, a bunch of updates that actually have to happen, which makes those integrated development environments nice. If you've ever had a pleasure of working with one of these, sometimes they're proprietary, sometimes they're like Microsoft Studio or something, or sometimes they're tools, Bugzilla, stuff like that, that actually does tracking stuff for you and automates the process. Because programmers won't document anything unless you have to. And then you want to make the job easier. So some of the documentation that's involved with testing is the plan itself, the test specification, and the evaluation. The test descriptions, believe it or not, that are often left out. Why do you want to, describe something? You already know what it does. But a year from now, when you have to go back and regression test something, a description is nice because you might not necessarily remember all of the tests that you created. And then your test analysis report, the final deliverable of all of the results, should be documented somehow as well. All of this should be archived. Some of it's handed to the users, to the people who bought the software. Some of it's left for the development team. Some of it's left for the program, different audiences for different documentations as well. So what is this? A note on user interface testing. User interfaces need two categories of testing: design and implementation, and then also acceptance at the end there. But during the design phase, the user interface testing is carried out with trial users, hopefully to ensure that the design is usable. You can find the options. Sometimes, in terms of the implementation phase, it goes through standard steps, unit testing, tests back. Sometimes, most of the user interface testing is done by external people, focus groups. In fact, used to be popular, not so much anymore, but you could do like part-time jobs actually to test user interfaces. You'd show up at a company, they'd give you a program and tell you to, create a document. So you go and you look for the open, or you try to figure out to see how intuitive the program actually is. Now everything is kind of following the same model these days. All Windows programs look the same. Mac programs look the same. So we don't have as much variety. But I suspect as soon as people get bored with everything, we're going to come back. We're going to start doing this again, where we have some innovative kind of designs. But when innovation kind of died, so did focus group stuff, focus testing. But the goal is to actually kind of see from the design perspective: do you have things in the right places? Is the interface usable? Can users find the tools and things? And then are the metaphors appropriate? You have a little scissor for cut. Does it look like a cut? And the paste, is it a bottle of paste? I don't know what they use for paste, but I don't think it's a bottle of paste. That wouldn't go over. And then in the implementation phase, the user goes through standard steps of the unit to test for reliability for the implementation. And then we have the acceptance testing that's carried on the complete system itself. So. Fixing bugs. We all know about this, so I can kind of skip through this, right? Alright, so isolate the bug, understand the bug, fix the bug, different stages. And you might think, well, it depends on the language. It doesn't actually. You can apply a universal methodology to fixing bugs, regardless of the programming language that you're using, or the programming environment. So in terms of isolating the bug, you're pretty much figuring out, is it something that's intermittent? Is it repeatable? Does it happen when we have a network connection, when we don't? Is it complex? Is it simple? Understanding the bug itself, the root cause, the dependencies associated with it, maybe the structural interactions, and then fixing it, the design changes, document changes, code changes that might happen. We're going through the same process. In terms of our isolating and our understanding, that's when we're putting priorities on stuff. Is it an easy one? It's not necessarily the ones that are the easiest to fix that are fixed first, because it's kind of like the difference between what's a symptom and what's a problem. So we have bug symptoms that come out where we have things that are wrong. And they might be little things, and people, you know, the novice person would say, oh, let's just fix all the little things. They're easier. Let's fix them all first. But then if you actually really analyze the situation, this is how things like Bugzilla and stuff like that, not really Bugzilla, there's another program out there that does this. It takes and tries to figure out what module, you know, which one should be done. It tries to put a priority given the logic. If it knows how your source code is arranged, and if it's a development tool that's working with your code, then it can kind of see that this symptom, and this symptom is all related to this problem. You fix the problem up here, and it corrects all of these little symptoms, and it fixes all the other bugs, which is kind of a weird phenomenon, because people go, you know, like when you're writing your first program for your first programming class, you go, oh, if I fix this problem, if I just make it a float instead of a double or something, oh, it works. All of a sudden, all the other problems are fixed. You had a whole list of stuff you had to fix, but you fixed one thing, you know. Same thing happens though with regression testing. I fix one thing, everything else breaks. But long story short, your bug information can tell you the priority of what you want to fix. So, moving the bugs around, another problem, actually. You know, you fix it here, but it's broken there. So fixing bugs is an error-prone process, which is why we say the longer we maintain software, the more we wear it out, the more it actually wears out and becomes unusable. What is all that noise? I heard some people like yelling and screaming, I don't know. Like did they won a contest or something outside? And as soon as I say that, the noise goes away, obviously. All right, so fixing a bug is an error-prone process. When you fix a bug, you fix its environment, hopefully. The bug fixes need static and dynamic testing. And you repeat all the tests that have a slight relevance, hopefully using some sort of regression testing methodology. And you keep in mind that just because you fix one thing, it may not necessarily have broken another. And the more you fix, the more you ruin the original integrity of the code, which is how code decays and code wears out. And bugs have a habit of returning, actually, if they're not fixed correctly. And it's kind of like how you have a leaky hole in a hose, and you put a piece of duct tape on it, you put a piece of tape on it, and then the hole comes back because the tape wears out, the sun hits it, dries up, the tape's not effective anymore. Same thing actually happens with software. So you fixed it so that the log file got purged every week. And then lo and behold, the volume of the sales comes back up, and now the log file needs to be purged daily. So you actually have to kind of keep a history of what you fixed. Because if you didn't know that somebody last year adjusted the log file timing, you might take hours and days and weeks and months, and you might fix everything else in the world. But if you had known that somebody else had adjusted the log file timing a year ago, and now the same problem has come back, it might give you some insight. So the history and the documentation might actually help you with future bugs, because once you fix a bug, it's not gone. I mean, it might actually come back, and keeping that in mind will actually help you become more efficient. So when a bug is fixed, add the failure case to the test case as well for the future. So even though, it works now, doesn't necessarily mean it won't work in the future. So security in the software development process, which is kind of a different concept here. Let's see, hold on one second. Let me take a look what I've got here, because I'm thinking that this is the end of the of the testing information, and I think it's probably, I'm looking at my clock now, 2, 3, 30, probably a good stopping point, I think, as well for today, because I have more testing stuff, but it's in a different lecture, and now this is kind of getting, I forgot that this set was kind of split into 2 different concepts, which really makes nice for 2 separate lectures. So I believe what I'm going to do is stop today at this lecture here, at this point, write it down so I remember, talk about security issues as associated with the testing environment, and I've got some more testing stuff for you, actually, for next week as well, in the following lecture that precedes this in the lecture set. Any questions? If you weren't here in the beginning, I made a couple announcements. One of them is I'm going to talk about the midterm next week, so it's not available yet. The midterm is a take-home and is not an in-class exam, contrary to popular belief. Your final exam will be an in-class exam, closed book, closed notes, closed neighbor. Your midterm is going to be something where I'm going to give you an exercise. It's not going to be answering multiple choice questions. That's probably going to be the final. Your midterm is going to be like doing, putting together something as an exercise. I'm also going to have your CSLO essay ready to go here. And it's not like last year's CSLO essay. It's a totally brand new concept. That one won't be due until the end of the term. Your midterm will be due in about 3 weeks or so. I will have the midterm. I'll explain the requirements, expectations for it next week. I'll have it available electronically next week. I'm just giving you the timing on it today. And if there's a problem with you uploading it, don't panic, don't worry. I'm not going to count it late, but we would like to kind of get it in as an assessment prior to the end of the term rather than waiting to grade everything at the end of the term. So I will see you all next week.